If you remember from college algebra, we have found vertical and horizontal asymptotes as well as x and y intercepts. So jumping right in with our warm-up question, if we want to find our vertical asymptote, we know that it's down here. Oops, let me adjust this. This is our vertical asymptote. So if you set this equal to 0 and solve, you get x equals 5. Moving on to the next part, if we solve the numerator, we get our x-intercepts. In this case, we only have one, so 3x plus 24 equals 0, 3x equals negative 24, and x equals negative 8. So you have an x-intercept at negative 8, 0. If you look at the beginning, you have your horizontal asymptotes. Here, our powers match, and so we're just going to simplify those coefficients, and we'll get 3. Last, if you look at the terms at the end, you have your y-intercept, which is going to be 0, comma, 24 over negative 5. If you want to simplify that, you can. It doesn't really ask at that this part of the question. Okay, that's all of the pieces that you need. Now, talking about arrow notation, this becomes important in calculus, and we really want to highlight that directionality. So right here, 0 with that plus sign means coming in from the right. So this is from the right. So the way that you would say this is as f of x approaches infinity, sorry, f of x approaches infinity as x approaches 0 from the right. I'll say that again. As f of x approaches infinity as x approaches 0 from the right, which makes sense. Y goes up to infinity as x is coming in to 0 from the right side. So as we come into from the right, y goes up. Over here, we're saying from the left. From the left. Same situation. F of x approaches negative infinity as x approaches 0 from the left. So that means y goes down as we approach 0 from the left side, which again makes sense visually. Remember from college algebra, we've always found vertical asymptotes. It's what kind of cuts the function down the middle, and you're never going to touch that line. That's always from your denominator, right? We did that in the warm-up. We know that when the denominator equals 0, the function doesn't exist, right? We can't have a denominator of 0. So that is where we have our vertical asymptote. So in this example, we know that x plus 5 can't equal 0. So x can't equal 5, negative 5. And so that's where you have your vertical asymptote. There's your dashed line at negative 5. The new thing that we're covering in this section is the removable discontinuity, or what we call a hole. In calculus, you're going to use both of these quite a bit. So for a hole, what's going to happen is you'll get it in factored form, and you're going to notice that the top and the bottom have something in common. In this case, they have an x plus 1 in common. Okay, that means they cancel out. Because if you were to leave it, right, and you plugged in negative 1, the function would end up being 0 over 0, and we can't have that. So if we have x plus 1 equals 0, we find that x equals negative 1. This is what we call the x-coordinate of your hole. So this is the x-coordinate of hole. The function can't exist in the current format. It can, however, exist as f of x equals x minus 2. Once you get rid of this, you now have a function that works. However, you still need to account for the fact that there is some sort of gap when x is equal to negative 1. So if you plug in negative 1, you can find the hole. This gives you a y value of -3. So the whole is going to be at -1, -3. What you end up graphing is this. And on that line, here is where you have an open circle. So notice on this figure, you're continuous, you're continuous, you're continuous. Oh, there's a gap, and then you're continuous, continuous, continuous. That's what's going to happen at this point. You're going to have this linear expression. You're going to have a solid line. Oh, -1, -3, and then you're going to go on forever. That right here is -1, -3. We'll do a couple practice problems where you'll see this happen. Let's briefly touch base on horizontal asymptotes. There were two kinds. There was one where it was 0, and there was another one where it was a number. So here, you'll notice that you have x squared in the numerator and x cubed in the denominator. This means that your horizontal asymptote was 0. So the numerator power was less than the denominator power, so y equals 0. That is from college algebra. Here, your powers are the same. Okay, if they match, the numerator equals denominator's power, then you're going to simplify the coefficients. So in this case, y equals 1/2. Let's say simplify coefficient. Okay. What we haven't talked about, which I casually mentioned in college algebra, was that slant asymptotes also exist. Okay. That's when there's a difference of degrees of exactly 1, with the higher one being the numerator. So here the numerator power is greater than the denominator. Okay. So that would be like an x cubed over an x squared. Any sort of version of that. Exactly 1 higher. We can do that by using synthetic division. So if you do synthetic division, you can find the equation of that slant asymptote. Your denominator gets solved for x, and that's what goes in your little box. And then in your long rectangle, you have all the coefficients of the numerator. So 1, 2, and -2. Bring down the first term, multiply, add that up, do it again. But really, this column is irrelevant. Okay. This is so small, it's negligible. Okay. So you can ignore it. All we want is y equals x plus, right? Everything drops power. This right here is your slant asymptote. It's a line. Okay. It's always going to be a line when we're doing these. I would encourage you to pause the video and do the next one on your own. So now we have -2 in the little box and 3, -4, and 1 in the long rectangle. Bring down the 3, multiply. The last one doesn't matter. We have y equals 3x minus. There's your slant asymptote. Again, it's just a line. Now let's go into putting all this together and find intercepts, asymptotes, and a graph. This one is a little bit trickier than some of the other ones you're going to see. So I'll just go ahead and say that now. You won't have something this complicated on your test, but it introduces another concept that will be important for calculus. So step one, I am going to go ahead and factor the numerator and then factor the denominator. So I have 2x to the fourth minus 10x squared plus 8. So this is a power 4, so I'm going to use u substitution again. I'm going to say u equals x squared. Now I have 2u squared minus 10u plus 8. I'm also going to just factor out a 2 because I want to use the smallest numbers possible. And now let me factor. I have u minus 4 and u minus 1. I'm looking for factored form, so this is where I stop. Let me go ahead and replace everything back with x squared. And here is the factored form of my numerator. Let me do the same thing for my denominator. I have x cubed minus 3x squared minus x plus 3. Here I can group. I have x squared in common, x minus 3 inside, negative 1 in common, x minus 3 inside. We have x squared minus 1 and x minus 3. This is factored. Okay, let me now rewrite this function in my factored form. And I'm just going to duplicate. We have that over that. These are the same two equations. This one right here on the right is just factored, which means I get to see a lot more stuff. With that, I'm going to notice that here is what cancels out. This determines my whole. So let's start writing this again. If I get rid of it, I have 2 times x squared minus 4 over x minus 3. This is the equation I'm going to find everything else from, okay? This is what I'm going to reference now. Okay, this is my new function. Okay, I'm no longer using the original. I need to find my whole or wholes. Okay, I said x squared minus 1 cancels out. So that means x squared equals 1 or x equals plus or minus 1 because we take a square root. So I'm going to have two wholes. I'm going to have 1 comma something and negative 1 comma something. Let's go ahead and find the y value to the wholes. That means I need to plug in to my new function my 1 and my negative 1. So when x is 1, I have 2 times negative 1 squared minus 4 all over, whoops, that should be a positive 1, 1 minus 3. Okay, so that's 1 minus 4 is negative 3. Negative 3 times 2 is negative 6. Divided by negative 2, I believe, is 3. I need to double check that math. I feel like I did that too fast. Give me 1 second. Mm, 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 mm. Okay, that was right. Okay, and then when x equals negative 1, I have 2 times negative 1 squared minus 4 over negative 1 minus 3. And that'll be, I believe, 3 halves is what it was. But I'm going to double check that, so maybe don't write that down yet. 1 minus 4 all divided by negative 4. Yes, I was right. 3 halves. So we have our wholes now. 3. Now we need to find everything else. Okay, wholes are new, so that's now done. I'm going to shrink this a little bit so I have room for all my other stuff. So we've done the wholes. Let's work on our vertical asymptote. We can do the vertical asymptote really easily. That just means setting the denominator equal to 0. Going to be 3. Let's find our x-intercepts. That means let's distribute the numerator. We have 2x squared minus 8 equals 0. And let's solve the numerator. Okay, that's going to give us x is equal to plus or minus 2. So that means we have 2, 0 and negative 2, 0 for our x-intercepts. We've done that before. Let's look for our y-intercepts. That's going to be, so let me rewrite this, 2x squared minus 8 over x minus 3. Okay. That's going to be this right here, simplified, 8 over 3. So 0, comma 8 over 3. If you want to do a decimal, you can. 8 over 3 is about 2.6 repeating. Okay. All right, now all we have left is our slant asymptote. Okay. Let me shrink this also a little bit so we can move it out of the way. Go there, go here. That way I have the function right in front of me. Okay, so now we're going to work with our slant asymptote. We have y equals 2x squared minus 8 over x minus 3. 3 goes in the little box. We have 2, 0, and negative 8. Remember, the 0 is here because we do not have an x term, and we want to show that we don't have an x term. Bring down the 2 and multiply. The last column doesn't matter. So our slant asymptote is 2x plus. Now we put everything on the graph. Okay. It doesn't matter what order you do this in. I am going to color code this. So I'm going to start with my slant asymptote. I'm going to go up to 6. 1, 2, 3, 4, 5, 6. Up to over 2. Okay, so that's enough for me to kind of know what this is going to look like. So I'll draw my dashed line there. Oops, let me make that a bigger line. There we go. Okay. And then for my vertical asymptote, I have a 3. So let's go over to 3 and draw that line. And then let me extend it a little bit. There we go. We'll do our x-intercepts. 2 and negative 2. So there's 2 and negative 2. We'll do our y-intercept. 2.67, so like roughly there. Okay, let's do the holes. I'll do those in orange at 1, 3. And I'll make this thinner so you could really see that it's an open hole, open circle. And then we have another one at negative 1 and 1.5, so here. Okay, so what you should start noticing is over here, you have a lot of points that are starting to create some curvature. That's good, right? That means you're on the right track. So let's put this all together and graph. So here that combines, that's going to go down, all combines, and that goes down. Now, it's hard to tell on this graph, but this is going to continue upward. So if you were to continue this dashed line, your curve would reflect, whoops, over this corner. I'm not super concerned about this, right? You just need to draw a general sketch. You don't have to plug in points over there, but the other side does exist. So you have all the points here, and then you have a reflection up there in the corner. Okay? It doesn't need to be super perfect, but that's everything you would need for this graph. Let's do another one. Same process applies. Like I'm just going to, that should be a squared. I'm just going to go ahead and factor the numerator, x cubed plus 2x squared minus x minus 2. We have an x squared in common, and then we have a negative 1 in common. So we have x squared minus 1 times x plus 2. So that's your factored form for that one. And then for your denominator, x squared minus 4 is the same thing as x plus 2, x minus 2. So writing that all together, we have x squared minus 1 times x plus 2 over x minus 2 times x. You should immediately notice that you do have a hole in the graph. It's going to be at -2. Okay? We have a hole where x is -2, and we need to find the y value for that hole. So our new function that we're working with is going to be x squared minus 1 over x minus 2. If we want to find our y value for that hole, let's plug it in. So we have -2 squared minus 1 over -2 minus 2. So that's 3 over -4. So your coordinate is going to be -2, -3/4. Okay, so that's the hole. Now we can find everything else. Same as before, the vertical asymptote, easy breezy. We'll set the denominator equal to 0 and solve. Our x-intercept, we'll set the numerator equal to 0 and solve. We'll have two x-intercepts like before. So 1, 0, and -1, 0. And then let's do purple. Um, oh, our y-intercept, we could do y-intercept. That's going to be 0, 1/2, because -1 and -2 will will cancel out negatives. And then finally, we'll do our slant asymptote. So in our box is going to be the 2. In the rectangle, we have 1, 0, -1. Again, we don't have a middle term, so we want to show that with a 0. Bring down the 1, multiply, and add. The third column doesn't matter. So our slant asymptote is x plus 2. Now we have everything we need, and let's graph it. So if I start at 2 and then I just go up and over 1, I can draw my asymptote. Oop, not very straight. Oh, that worked out nicely. My vertical asymptote is in pink, so let me switch to that really quick, and we'll draw that. My y-intercept is 1/2. We'll zoom in, there it is. Oops, move back to solid. My x-intercepts are 1 and -1. So 1, -1. And let me draw the hole. It's going to be at -2 and 3/4. So right around here. Okay, that's going to be an open circle. And now I have everything I need in order to draw the curve. Similar to before, you'll start to see that curvature in this corner where and up here, you're just going to kind of wing it, draw a little curve, and call it. Okay? Last but not least, a quick refresher on writing the equation for a graph. My suggestion is to write down everything you know about it, right? You know your vertical asymptote, horizontal asymptote, your x-intercepts, and your y-intercept, and then we'll go from there. I believe there are two of those, so let me make some room. So one of your vertical asymptotes is x equals 4. The other one is x equals -1. The horizontal one looks like 2/3. I'm gonna put a little question mark there. It isn't quite 3/4. I think it's 2/3. X-intercept is gonna be 2, 0 and -3, 0 right here and right here. And my y-intercept is gonna be 1. So from there, I'm gonna set up my equation. I know that my denominator represents my vertical asymptotes. So I'm going to go ahead and write them in factored form. I know my numerator represents my x-intercepts, so I'll write those in factored form. Okay. I also know that my horizontal asymptote is represented in the front. If it's not zero, it means the powers match. So that makes sense to me, and that's where they're going to go. I'm also not 100% sure that I've got everything, so I'm going to put my A in there in case I haven't gotten it all. Now, the last thing I need to do is to confirm that my y-intercept is going to be 1. So this is where I plug in 1. I say 1 equals 2a, 0 minus 2, 0 plus 3, all over 3 times 0 minus 4, 0 plus 1, right? This is the coordinate 0, 1, and I'm plugging those in. Once I do that math, I get negative 12a over negative 12a, negative 12. That means a is in fact 1, and everything I wrote in black is correct. So the equation for this graph is going to be 2 times x minus 2 times x plus 3 all over 3 times x minus 4 times x plus 1.